Hello everyone. Welcome to the 22nd video of our lecture series. So in this video, we are going to discuss about Schrodinger equation in spherical coordinate. So, so the generalization of this Schrodinger equation in 3 dimension is quite straightforward. So what the Schrodinger equation says, it says that IH curve, the time evolution of our wave function, is given by this. So where we have our classical Hamiltonian operator. So in case of 1 dimension, it is just p square 2m plus our potential energy. But in case of 3 dimension, we have our Hamiltonian to be px square. So if it is in Cartesian coordinate, then it will be py square pz square by 2m, and we have a potential which depend on x, y, and z. So this is our Hamiltonian, and and now we have our wave function, which is a function of x, y, z, and t. So now the probability of finding the particle in an infinitesimal volume will be given by, so let us write down the probability of finding the particle So in case of 1 dimension, as we have talked about, probability of finding between an interval. But here we have 3 dimension, so we will talk about probability of finding in a volume element. So the probability of finding in the infinitesimal volume element dq bar, which is dx, dy, dz. So now the probability will be psi RT square dq bar, and now the normalization condition will be psi squared dq bar. So we have our integration over all the 3 coordinates, so this will be 1. So this is in our general formalism for any 3 dimension. Now for most of the cases, we have the potential, which is a function only of the distance from the origin. So typically we have a potential which is a function only of the distance from the origin. So if that is the case, then it is quite natural to adopt spherical coordinate. So then it is quite natural to adapt our spherical coordinates, that means r, theta, and phi. So now in spherical coordinate, how does our Laplacian look? So Laplacian, this looks like in spherical coordinate. So this is a standard result. You will find this in any standard mathematical physics textbook. So it is given by 1 by r square del r square del r plus 1 by r square sin theta del theta sin theta del theta, and we have our last term as 1 by r square sine square theta del 2 del phi squared. So this is our Laplacian in spherical coordinate. So how does our Schrodinger equation look in spherical coordinate? So it will look like minus h cut square by 2m. We have 1 by r square del r square del psi del r plus 1 by r square sin theta del theta sin theta del psi del theta plus 1 by r square sin square theta del 2 psi del psi square. So this is our first term, plus we will have our potential and psi, and in the last term we will have E psi. So typically we will begin our problem. So we have to solve this equation. So we will look for solution that are separable into product. So we begin by looking we are assuming that our solution, they obey the separation of variable rule. So we can write our wave function psi r theta phi as a function of r and as a function of theta and phi. So we are making separation of variable of a radial coordinate and angular coordinates. Now if we put this in our equation, so let us denote this by 1. So we are putting this in our equation 1. Then what we will get? Then we will get minus h cut square by 2m y by r square d dr r square dr dr. So here we have partial derivative and here we are writing total derivative. So why it is so? So because we know that r only depends on radial coordinate. So r doesn't depend on theta or phi. So del r and dr they will lead to same quantity. But del psi del r and d psi dr they are different because psi depend on all three coordinates, and so that is why their total derivative and partial derivative, they are not same. But if our function only depends on this variable, then the total derivative and partial derivative, they will lead to same result. So that is why we are replacing our partial derivative by total derivative. So our next term will be r by sin square theta r by r square sin theta del theta sin theta del y del theta. So here we are reading partial derivative because y depends on both theta and phi. So that is why we are keeping we have to keep this partial derivative, and our last term will be r by r square sin square theta del 2y del phi square. So this is our first term, and second we have v into psi, but psi is r into y, and our last term is e into r y. So this is what we get from our Schrodinger equation. So let us denote this by 2. So now divide 2. So what we can do? So we can divide it by ry, and we are multiplying it by minus 2m r square by h cut square. So if we do this, then we will left with 1 by r ddr r square dr minus 2m r square by h cut square. Here we have v minus e plus 1 by y, 1 by sine theta del theta sine theta del y del theta plus 1 by sine square theta del 2y del phi square. This is 0. So this is what we are getting if we if we divide this equation by ry and multiply by this. Now if we notice carefully, then this term only depends on r, and this term, it depends on theta and phi. So suppose our theta is changing, so then this term will change, but this term is equal to the negative of this term, so that is not possible. So that is why both of the terms must be equal to a constant. So let us now choose this constant. So these are called separation constant. So let us choose this separation constant to be L into L plus 1. So reason for this will be cleared later. So if we choose this, then we have these two following equation. So 1 by r ddr r square dr minus 2m r square by h cut square v minus e, which will be equal to L into L plus 1, and we have another term. So 1 by y, 1 by sine theta del theta sine theta del y del theta. This is our first term, and we have 1 by sine square theta del 2y del phi square. So this must be equal to minus of L into L plus 1. So this is our radial equation, and this is our angular equation. Because this equation only involves our radial coordinate, and this equation it involves both the angular coordinate. So that is why they are named so, radial equation and angular equation. So let us first now deal with the angular equation. So what is our so in our angular equation, if we multiply our angular equation by y sine square theta, then we will get sine theta del theta. So our goal is to now again separate these two variables. So that is why we are what we are trying to do. So this will be sine theta del theta sine theta dy d theta plus del 2y del phi square, which is equal to minus of L into L plus 1 sine square theta y. So we are getting this. So this is a standard equation. So it occurs in the solution to Laplace equation. So basically, if you have studied classical electrodynamics, then you will see that this occurs in the solution to Laplace's equation. In classical electrodynamics. So what we have previously said, so we will again try this separation of variable. So we want to separate these two variables, so we will denote this by capital theta, which is function of only theta, and we have capital phi, which is function of only phi. So if we put this in our this equation, then we will get 1 by phi. Here we have sin theta, d theta, sin theta, d theta, plus L into L plus 1 sin square theta. So this is basically our first term, and we have second term to be 1 by phi del 2 phi d2 phi d phi squared. So we are replacing our partial derivative by total derivative, because phi and psi, capital phi, capital psi, they are function of only theta and phi. So we can replace our partial derivative with total derivative. So if we notice carefully, so this is only a function of theta, and this is function of phi. So like the logical region what we have provided for the previous case, so for that reason these two terms also must be equal to a constant. So this time we our separation constant, so let us denote this by m square. So if m square is a separation constant, then we are left with these two following equation. So we have 1 by theta, and here we have sin theta, d theta, sin theta, d theta, plus L into L plus 1 sin square theta, and here we have m square. So this is one equation, and another one which we will get is 1 by phi d2 phi d phi square, which will be equal to minus m square. So we are left with these two following equation. So if we notice carefully that this equation, this solution is easy, so phi equation is easy. So what we have? So we have d2 phi d phi square equal to minus m square phi. So what will the solution look like? The solution will be, so phi, which is a function of phi, is e to the power I m phi. So now, so we know that what phi represents. So in space, we know that when phi advances by 2 pi, so we return to the same point in space. So we have this coordinate system, and this is our phi. So if phi advances by 2 pi, then we return to the same point. So that means we must have our phi, we must satisfy this condition. So phi plus 2 pi, it should be equal to phi. So what it will lead to? So it will lead to exponential I m phi plus 2 pi. It should be equal to exponential of I m phi. So our exponential I m 2 pi must be equal to 1. So what does this represent? So this represent that m, it must be an integer. So m is 0, plus minus 1, plus minus 2, and so on. So this is our solution of phi equation. So let us solve our theta equation. So we have our theta equation as this: d theta sin theta d theta this plus L into L plus 1 sin square theta minus m square, and we have here theta. So this is 0. So this is a standard differential equation, first order differential equation. So this is known as legendary polynomial equation. So the solution of these equations are, so you will find this in any standard mathematical physics textbook. So solution is A P M L cos theta. So what does this PLM represent? So this is associated legendary function. So how is this? How this is defined? So this is defined by PLMX can be write down as 1 minus x square mod value of m by 2 d dx m and PLX. So where this PLX, this is Lth legendary polynomial. So now this we have to know the definition of this PLX. So the definition of the PLX or legendary polynomial, it is defined by Rodriguez formula. And what is this? So this is basically PLX. It is 1 by 2 to the power L factorial ddx L x square minus 1 to the power L. So for example, so if we are given with an example, it will be clearer. So P0x, so it will be 2 to the power 0 into 2 factorial ddx of 0 x square minus 1 to the power 0. So that will be 1. And what is P1x? So P1x is basically 2 into 1 factorial ddx of x square minus 1. So it will be just x. And in this way we can calculate all this. So P2x is 4 2 ddx square x square minus 1 squared. So that will be half 3x square minus 1. So in this way we can define all our legendary polynomials. So if we know our legendary polynomial, and if we plug down here and put value of m, then we will find the value of our associate legendary function. So for example, so this P20x, this is half 3x square minus 1, P21x, so that will be 1 minus x square to the power half ddx of half 3x square minus 1. So that will be 3x root under 1 minus x square. And similarly P22x, it will be 1 minus x square, and here we have double derivative of half 3x square minus 1. So this will give us 1 minus x square, and this term, like so when we apply first derivative, so it will be 3x, and when we apply second one, so it will just be 3. So in this way we can define all our so in this way we can calculate any PLM X. So this is the solution of our theta equation. So now we know that volume element in spherical coordinate. So we have to find this term A. So for that we need. So how can we find this? We can find this by normalization condition. So for normalization condition, we know that the volume element in spherical coordinate is defined as r square sine theta dr d theta d phi. So from normalization condition, we have, so this is our wave function, and we have our dq bar, which is r square sine theta dr d theta d phi. So that should be 1. So this is and now psi can be write down as r square, and here we have r square. So this is our r, and we have y squared sine theta d theta d phi. So this is on theta and phi. So it is convenient to normalize this r and y separately. So we have two normalization equation. One is r square dr, which should be 1, and we have theta integration. So for phi limit is from 0 to 2 pi, and theta limit is from 0 to pi, and here we have y square sine theta d theta d phi. So these two separately should be 1. So if we proceed and do our normalization, then our normalized angular wave function, or YLM, that will be defined by epsilon root under 2L plus 1 by 4 pi. Here we have L minus mod m factorial by L plus mod m factorial, and here we have e to the power I m phi p L m cos phi. So this is our normalized angular wave function. And what is epsilon? So epsilon is basically minus 1 to the power m. This is for m greater than 0, and epsilon is 1 for m less than 0. So this is our normalized angular wave function. So also for reason or from history, this L, this is called azimuthal quantum number. And m is called magnetic quantum number. So we are done with our phi equation, or phi theta equation, that means our angular equation. So now we have to solve our radial equation. So what was our radial equation? So that is our radial equation. So write down. So we have our radial equation to be ddr of r square dr minus 2mr square by h cut square, and here we have v minus e r, which is equal to L into L plus 1 r. So this equation will be simplified. So if we change our variable, so let us change. So we are defining a new variable u, which is defined in the following manner. So r multiplied with r. So if we do that, So now we will replace r by u by r, and what will be our dr? So it will be basically r du dr minus u by r square, and what will be our ddr of r square dr? So it will be basically r square d2u dr square. So if that is the case, then we can write our radial equation in the following manner. So minus h cut square by 2m d2u dr square plus v plus h cut square by 2m l into l plus 1 by r square u e u. So we can write this equation as minus h cut square by 2m d2u dr square plus v effective u equal to eu. So if you look carefully, this is analogous to our Schrodinger equation in one dimension. So minus h cut square by 2m del 2 psi del x square plus v psi equal to e psi. So these two equations are analogous. The only change is that here we, in place of v, where we have our effective potential v effective. So this v effective potential, it is defined as So if we are given with a potential, then we have to add the term, then it will become our effective potential, and for that effective potential we will solve our one-dimensional Schrodinger equation. So this extra term, or this is called centrifugal term. So these are like standard textbook notation which we used. So this is our centrifugal term. So what we have our normalization condition to be r square dr 1, r is from 0 to infinity. So that condition will now become 0 to infinity u square dr. So this is our corresponding normalization condition. So which is which should be for a one-dimensional case. But for one dimension we have from minus infinity to infinity, but here we have 0 to infinity. So this is the only subtle difference. So unless we are provided with a potential form, so up to this we can go. Now if we are given with a potential form, then for that we can try to solve this radial equation. So in the next video we will solve we will solve our hydrogen atom problem. So for that we will be given a potential. So it is of the form minus 1 by 4 pi epsilon naught e square by r or something. So if we have this potential, then we will try to solve our radial equation, and we can get our wave function of hydrogen atom, and we will do our an analysis. So that is it for today's video, and we will meet on our next lecture video. Thank you.